Welcome back to Integral Calculus. In this video, I want to review the derivative. We'll start off with notation. If we have a function, generally something like y equals f of x, or if we want to be more technically correct, we can talk about the function f, which maps from the domain of all real numbers to the range of all real numbers. Then the derivative of this function is going to be f prime, which will again map from the domain of real numbers to the range of real numbers, or some subset thereof. I'm not that worried about the details. But you can also think about this as f prime of x, or if you prefer, df dx. There are subtle differences in the meanings of these two notations. I'm not going to quibble about them. They're not that important for this course. They may be important for a future course that you take if you're going to continue on your journey in mathematics, but we're not going to spend that much time talking about the derivative in a course called Integral Calculus. One of the key ideas of the derivative, my favorite explanation of the application of the derivative, is thinking about analyzing graphs of functions. So if I have a graph here, y equals f of x, and I have a particular point of interest, let's put it right here and call it x equals c, then I might want to draw a line tangent to the graph at that point. And the equation of that line is going to be y equals x minus c times f prime of c plus f of c. I kind of ran out of space there on the side of the screen, but you get the point. X minus c times f prime of c plus f of c. And so if we can know some things about the function, we can get the tangent line, and the tangent line is useful in a number of purposes, not the least of which being a nice way of approximating things so that you can work backwards and solve an equation that you might not have been able to otherwise. All right. That's all well and good, but how do you take a derivative? Well, again, remember there's a couple of different approaches. You may or may not remember the limit definition of a derivative. There's a couple of different versions of this. F prime of c is the limit as x approaches c of f of x minus f of c all over x minus c. Or maybe you remember that f prime of x is equal to the limit as some delta x goes to 0 of f of x plus delta x minus f of x all over delta x. And yes, technically that is how you take a derivative, but no one ever does it that way in practice. Instead, we tend to use the limit, or the differentiation rules. So we have things like the derivative of x to the n is equal to n times x to the n minus 1. That's the power rule. That works for any whole number or rational or integer value of n. Actually, it works for, actually it works for all real numbers, but technically you're not supposed to have learned that yet. Then you have the product rule. The derivative of f of x times g of x is equal to f prime of x times g of x plus f of x times g prime of x. You have the quotient rule. The derivative of f of x over g of x is equal to f prime of x times g of x minus f of x times g prime of x all over g of x squared. And then you have the chain rule. The derivative of f of g of x is equal to f prime of g of x times g prime of x. Oh. There's a couple of other differentiation rules that you probably should know. The derivatives of the trigonometric functions sine, cosine, tangent, and secant are useful. Cosine or cotangent and cosecant also could be useful, but not nearly to the same extent. If you know any others, that means that you're actually ahead of the curve right now. But let's go ahead and take a look at an example. Here I want to take the derivative of the square root of 3x plus 5. When I look at this particular expression, what I immediately see is that we're taking 3x plus 5 and raising it to the 1/2 power. Well, you can think about that as, say, f of x equals x to the 1/2 and g of x equals 3x plus 5. And then this is the composition. F of g of x would be 3x plus 5 to the 1/2 power. Do you have to write all that out? No, absolutely not. But it's a lot harder to see than it is to talk about. But because of that, I know that the derivative here, I'm going to need to know f prime of x. Well, the derivative of x to the 1/2 by the power rule is 1/2 times x to the 1/2 minus 1, which is 1 over 2 times x to the 1/2, or 1 over 2 square root of x. I'm also going to need to know the derivative of g of x. G prime of x is, well, just 3 in this case. So to take this derivative, I'm going to take f prime and evaluate it at g. So that's 1 over 2 times the square root of g, which is 3x plus 5, multiplied by g prime of x, which is 3. That'll just end up in the numerator. So my derivative in this case is 3 over 2 square roots of 3x plus 5. Let's take a look at one more. I'll do this in yellow as well. How about the derivative of 3x plus 1 over 2x minus 1? In this case, when I'm looking at this, the thing I see right away is that if I let f of x be 3x plus 1 and I let g of x be 2x minus 1, then what I'm really dealing with is f of x over g of x. Again, do you have to write that out? No, absolutely not. But if you find it helpful, then go ahead and do so. Writing more is never a bad idea. Not writing enough is where you tend to get into trouble. All right. So this is a quotient. That means I'm going to use the quotient rule. In order to do that, I'm going to need to know that f prime of x is 3 and g prime of x is 2. So remember, the quotient rule tells us that the derivative of the rational is going to be f prime times g, 2x minus 1, minus g prime 2 times f, which is 3x plus 1, all over g, 2x minus 1 squared. There's a lot going on in the numerator, so it's probably going to be in our best interest to simplify a little bit. In fact, this one simplifies pretty nicely. We're going to have 6x minus 3 minus 6x minus 2, if we just expand out. And then 6x minus 6x cancel each other out, and we're just left with negative 5 over 2x minus 1 squared. And that looks like a good way to leave it to me. Yeah, we could multiply out that denominator. We could call it 4x squared minus 4x plus 1 if we really wanted to, but it doesn't gain us anything. It doesn't allow us a better opportunity to reduce the fraction or anything like that, so I'm just as happy to leave it at this. All right. One more example, and this is the one I would like you to try. So just as a nice quick warm-up here, I'd like you to think about the derivative of x plus 1 times the square root of x minus 1. All right, as they go, that's a little bit messy, but not as too bad. It's probably not as bad as the one that I just finished. But take a couple of minutes, see what you can do with that one, write it out, and I'll see you in the next video.